Okay, welcome everybody to the talk on NVMe Computational Storage. My name is Kim Malone. I work for Intel, and I am a participant in the SNIA Computational Storage twig that Jason and Scott just presented on. And I'm also the co-chair of the NVMe Computational Storage work group that I'll put in a plug for at the very end. So what I'm going to do today is take you through the architecture, or at least the high-level architecture for NVMe Computational Storage. So you just heard about the SNIA architecture, and you can think about the SNIA architecture as something that is on top, or the NVMe layer is underneath the SNIA architecture. And Bill Martin has a talk in 2 hours, I think, where he's going to be talking about how the two things work together and complement each other. So I'm not going to go into that, but they are related and compatible with each other. So the first main concept that you need to understand when it comes to NVMe Computational Storage is the concept of programs. And for some reason, we choose not to say programs instead of functions, because of course it has to be different, but you could think of them as basically the same thing. So what we've defined as programs are the computational storage offloads in NVMe. So the idea is that programs are invoked and used in a standard way. So they're conceptually similar to software functions. You call them with parameters. In the current incarnation, you call them and they run to completion and return a result. In NVMe, these programs operate only on data that is in subsystem local memory. And I believe SNIA is calling that FDM, but it's the same general concept that it's memory that is on the device, co-located or near performance-wise to where the compute and the data are. Programs run on compute resources on devices. And related to a question somebody asked earlier, these programs may be in hardware or software. So these could be implemented by a device as fixed function programs, meaning the device provides these. You can call it as a program, but it could actually be implemented in hardware, an FPGA or something like that. The other option is a device may offer downloadable programs, and that would be something where a program is written and the host downloads that program to the device, and then it can be called in the same way that the hardware ones can be called. One other thing to note is that a program may only be able to execute on a subset of the compute resources in an NVM subsystem. So you may have heterogeneous compute resources, and certain programs may be able to run on some devices and not others, depending on what it is that they support. So to go a little bit more into downloadable versus device-defined functions, and device-defined is the term we're using for fixed function, meaning it's kind of encoded and unchangeable. So the standard supports both device-defined and downloadable. So device-defined are ones provided by the manufacturer that are not changeable by the user or the host. And they're callable as programs. They're callable in the same way that downloadable programs are. And this could be things like compression, decryption, things that are well suited to have a hardware implementation, things that are well known. So downloadable programs are, like I said, downloaded by the host. These could be things that are, written by an application or a user that do things that are a little less predictable. So let's say you wanted to run a filter function on a columnar data format. What you want to do might be different than what the next person wants to do. So you want to download your own program to do that. And I'll talk a little bit more about formats for downloadable programs in a minute. So downloadable programs provide a lot of things. They provide flexibility. You can process complex formats that might not be easily understood by simpler things. It's not just a contiguous range of blocks. It could be columnar data or JSON data or other formats of data. Downloadable programs can also be useful for emerging applications. So you could use a downloadable program to prototype something that maybe eventually gets encoded in hardware, but you want to try it out first. And so we can also have, when it comes to downloadable programs, the formats could either be vendor specific, so a particular vendor wants to offer something that only they offer, or we could also support things like well-known formats. eBPF is one, but there are other formats that could be supported as well. I think the idea is the format would have to be known in order for somebody to be able to write a program that can be downloaded to that device. So if you knew that it was the device supported eBPF, you can write an eBPF program and know that if you downloaded that, it's going to work. So eBPF, just as an example here, is something that it has a lot of, it's been around for a while, so it is well understood. There's a lot of ecosystem and toolchain stuff for it. You can write a C program and compile it into eBPF bytecode, and it is standardized under Linux. So that's just an example of the kind of thing that could be standardized as a format for downloadable programs. So let's move to the major architectural components for NVMe Computational Storage. So there's a picture here with a number of blocks in it. So what we have at the top in the orange is the host, and then everything below that is in an NVM subsystem. So this is just an example. It has like a single controller and a certain number of namespaces, but this is just meant as an illustrative example. There's no limitations implied by this picture. So what you can see on here is that there are 3 different kinds of namespaces. So we have the NVM namespaces that exist today that we already know and love. So there's the non-volatile memory namespaces. We have zoned, ZNS namespaces, and key value namespaces that are already defined today. And in this picture that is on the far right column, so it shows an example of a couple of NVM namespaces. What we're introducing new for computational storage is 2 different kinds of new namespaces. One is compute namespaces. So a compute namespace provides some computational functionality and can execute programs. The programs it can execute could be device defined, they could be downloadable, that would be discoverable at startup time. The other thing that is being introduced is the concept of memory namespaces, and that's the middle column. So we have memory namespaces here to kind of allow us to address and understand memory that is on the device. And these things all work together. So a program on a compute namespace operates on memory in 1 or more memory namespaces. And I'll go into some more of this. So let's talk about compute namespaces. So compute namespace is something that can execute 1 or more programs. It is a namespace that is associated with the new computational program's I/O command set. So that I/O command set is being defined in TP 4091. That's shown in blue here. And the programs may access data in 1 or more memory namespaces. And where the data is indicated when the program is executed. And you can see the compute namespaces in the diagram with the red box around it. Those are the ones we're talking about. So this new I/O command set is going to have a few commands that we've identified. The first one is execute program. So we have a program that's either already there because it's device defined or we've downloaded it. And the execute program command says execute this program on this data now. And that will run to completion and return a result. So they're not in a very good order for this, but the execute probably should be at the bottom. So first, if it's a downloadable program, you load program. That's a command you use to download it to the device. The next thing you may do is activate the program. So you've downloaded it, but you want now the program to be ready to run. So let's say you could download 10 programs, but only 2 of them can be runnable at any one time. So the activate program command is what tells the device that this is the one that I want ready, which means less latency when you go to execute because it's already ready to go. And the final commands are create and delete memory range set. And memory range sets are what we use to tell the device which memory this program is going to access. And that can be different on a per execution basis. And then finally, we add support for discovery commands such as identify controller and namespace that tells you things about these compute namespaces. For example, how many programs can you download to this thing? How many programs does it support? Which memory can it reach? That kind of thing. So the next kind of namespace that we're adding is memory namespaces. So memory namespace is a namespace that provides host command access to memory in the NVMe subsystem. So that is purposely worded like that. It provides host command access as opposed to direct host write access. It's not a load store memory. It is command access. You send read commands, write commands. So in that way, this is different than, let's say, CMB that already exists. We have talked about and will get to implementing some way of having a window into a PCIe bar or something if you want to map these things out. But that's not coming out with the initial release of it. Memory namespaces are also used by the computational programs command set in those compute namespaces to provide access to SLM, or memory for program execution. So the programs can only access memory that is in a memory namespace that they can access. So a program, as defined, cannot go to host memory and access memory there. So this subsystem local memory command set, this one is TP4131, so it has its own TP. And commands in this command set may include commands for reading from a memory namespace to host, writing from a host to a memory namespace, and also copying data between NVM and memory namespaces. So in order to run a program, you may want to copy data out of one of those NVM namespaces into the memory, run a program on it, program writes the output, and then maybe you want to put it back in an NVM namespace, maybe you want to read it to the host. And I have some flows to walk through for that, just to show you how that works. So here's an example of a flow to execute a simple data filter. So the first thing, and this is almost what I said a second ago. So the first step is to copy data into subsystem memory. So you can see here that some tabular data exists in NVM namespace 100. And the first command says copy the data from that NVM namespace into a particular place in memory namespace 10. So that data gets copied in, and a response goes back to the host saying that was completed successfully. So the next thing the host does is it says execute the program in slot 0 on compute namespace 1. So when that executes, as part of the parameters, the program is told where its input and output is, any other settings that it needs to know. And when the program runs, it uses the input is the data that was written, copied over from the NVM namespace. And the program output is, because this is a filtering program, it filtered and chose only the records where the state is New York. So the output is smaller than the input. And once the execution is complete, response is sent up to the host with potentially a return value from the program and whether the command succeeded or failed. So in this case, we have success. And in this case, the host wants to read the result back into host memory, as opposed to writing it persistently somewhere. So the host reads back from the place in memory back into host memory. And the host knows where in the memory namespace to read because it was the one that told the program where to put it. Once that memory is read back up to the host, we have success from the read command, and this flow is finished. So one thing to notice about this is, on a stepwise basis, this is very driven by the host. The host says, I want you to copy this data, I want you to execute this program, I want you to read it back, as opposed to it being more autonomous on the device side, that the device has to figure out what to do. So let's look at a slightly more complex, but very similar example. So this example filters encrypted data. So we're still doing filtering, but we're starting with encrypted data. So we have to decrypt it first before we can do filtering. So the steps are, like I said, quite similar. So the first step is to copy data from the NVM namespace into a memory namespace, except the data is encrypted. So we copy in, and you can see the data is encrypted. The next step is the host tells the device to execute the program in slot 1, which is a decryption program, and execute that against the encrypted data. So it executes, decrypts, and the output is the unencrypted table that we saw before. So after that step, because the host doesn't want to read back that data, it wants it filtered first. So the next thing it does is say, I want you to execute the program in slot 0, which is the filter program, against the data that was the output of the previous step. So it runs that execution. The filter program runs just like it before and spits out only the records with the state of New York. So then finally, the host reads back the output like it did before. So one of the things this shows you is, with this kind of architecture, you don't have to read back the interim data. You can have multiple steps go on it, and you only need to get back the result. Or the host can read it back at various points. The architecture works either way. So as I mentioned before, those of us working on this are in the NVMe Computational Storage task group. So I'm one of the co-chairs. Bill Martin, sitting up here, is also one of the co-chairs. And we have a lot of members, but we can always use more. So if any of you are interested in participating, help define this standard, you are very welcome. Please come and join us. Any questions?
A few slides back, the point where you had the host read out the local memory for the results, the New York.
Yep.
How did it know how much to read at that time? Is that in the completion from the step before, or some status that it has?
That's a good question.
Can you repeat the question?
I will. It was about this slide. So the question is, after the filtering happens, how does the host know how much data to read back? How many records? And the answer to that is, when the result is returned back, that can be one of the things. So it can be returned back as a result, Or alternately, it could also write that total size also somewhere in memory. The host could say, do this and like write the size here, and then the host would know to go read from there. But in this case, that's small enough to fit back. There's a 64-bit return code that you could use it for that. It was part of the reason why we did that.
For the memory namespaces, is there any requirement on access size or alignment or?
We were just talking about that last week. Yeah. So memory namespaces, let me go to the picture of that too. Back. So memory namespaces are a byte granular addressable. The accesses will be dword granular and dword annoyed, but the addresses are byte-based. Yep.
One of the things we're discussing is the fact that the memory namespaces are accessed from two different sides. They're accessed by NVMe commands on one side. Those are going to be dword aligned, dword granular. They're also accessed by programs. Programs are going to access the byte granular.
Did everybody else hear that? Who wanted to? So what Bill was saying, and that is correct, so the accesses I was talking about, dword aligned, are the command accesses from the host. However, the compute there is going to access it in a byte-wise basis. So we've been talking about how to capture and what rules to set with respect to them working together.
Anything about endianness, big endian?
We have not talked about endianness. Good question, though.
For data sets that are larger, fit into a particular namespace for an operation, have you considered supporting iterators or mapping constructs, or is it just left up to the application there to ensure parse through the entire necessary data set?
So the question was, for data sets that don't fit in a single memory namespace, are we considering providing iterators or some other way to go through the memory? That's correct. Do you have a particular size of data in mind, or just something that wouldn't fit into RAM on a single device? Is that what you're asking?
Well, I mean, this device would be shared. I don't know what the dynamics of how namespaces can be applied and created for it. But, yeah, I mean, it's more of a general question. Shared environment, limited resources.
Yep. So right now, we don't have that level of support for iterators or something like that. So at the moment, that would be on the implementer. However, there are APIs like the SNIA API that may be able to provide things like that. Unclear, just thinking about it, whether that would be provided at the NVMe level or provided at a higher layer than that. But one problem that needs to be solved by anyone wanting to do this kind of thing is, no matter how much RAM you have on a device, make it as big as you like, you'll still be a data set that won't fit in it, right? You always have to solve that problem somehow. So the simplest way, but puts the problem on the application, is to divide it up into pieces small enough that will fit into the memory. But yes, this is definitely something that I think we have some more discussing to do on it, but we don't have anything for that now.
The compute namespace doesn't
cost.
The way to do it would be to have that, though it was security goals, you could have an IO type command that could move data in from a fixed namespace.
So we don't have support for that today. So good request. What was the question? So the question was whether you considered having some kind of IO engine or mover on the compute namespaces that would move data in and out from an NVM namespace. Is that correct? That was the question. Sorry about that. So we did make a purposeful decision to not allow a compute namespace to directly access NVM namespaces at first, right? It's something we definitely need to discuss, but there are all kinds of considerations related to that add a lot of complexity. So in the interim, explicit commands are used to move things from NVM namespaces to memory namespaces, and then the compute ones can operate on that. But there's all kinds of controls that you have for things in NVM namespaces that you would have to somehow make work on the compute side, and it's not that we will never do that. We just decided not to bite that off at first. Do you have anything to add to that, Bill?
So the thing that's, you kind of alluded to, in the early stages of it is NVMe work in progress, is that there is a cross namespace copy command that can be sent to the device that allows you to copy from one namespace to another namespace.
Yes.
And that is what supports moving the data from the NVM namespace to the subsystem local memory.
Were you asking whether it needed to bounce through a host buffer?
I don't think it needs to go through a host.
No, it doesn't.
It could be commanded from the compute.
Got it.
namespace, right?
Yeah, the command needs to come from the host, but it doesn't have to bounce through a host buffer in order to do that.
I guess you envision that all these three namespaces will coexist on a NVMe subsystem. So you'll be able to kind of create them, have all three of them on the same device, be able to do inquiry and find out how many were there, create them, delete them. I think the coexistence part is something that's planned.
Yes, they can definitely coexist in the same NVM subsystem. In fact, that's part of what's intended.
Okay.
Not necessarily on the same device, but in the same subsystem.
Same subsystem, same device, I guess. And the host will be able to issue NVMe commands at the same time. It might be issuing some CS, I guess, commands to the new namespaces.
Yes, so
That are going to be the same queues. You see that happening over different queues.
So it would be the same queues. It's the same kind of queues. So the commands going to these, it's part of the reason why these are namespaces and not some other construct, is so that they can operate that way like namespaces do. So the commands are directed to a namespace, but they go into admin queues or IO queues as appropriate. And yes, they could coexist, and you can send commands to any and either of these.
Do you see them sharing the same NSID
No.
namespaces? Like, if one is used by the NVM subsystem, you cannot have a memory namespace using NSID1?
It's unique on a per controller basis, or is it per subsystem basis?
So every namespace has its own NSID.
Yeah.
So they will not share the same NSID between the different types of namespaces. In other words, and I'm not sure I'm addressing the question directly, but in terms of namespaces that are in the subsystem local memory utilizing that command set, those will have unique namespace IDs from any namespace in an NVM command set.
In the same subsystem, right?
Right.
In the same subsystem, right? So like if you have a namespace 100 in the NVM subsystem, there will not be another
Correct.
a different type of namespace.
Correct. The NSIDs need to be unique within the subsystem, even if the types are different.
One other, and it's a wide question. It seems to me that the memory subsystem is holding like data, and the program, the compute namespace is holding something that we're going to execute. Why not have just a memory subsystem with a different type? Was there a reason why you guys decided to have two different types of namespaces? Because essentially it seems like one has the execute compute type of, right? It's like what we have to execute information on a memory page versus data. I was just wondering why not just have a memory, a namespace, and then be able to make a distinction some other way.
So the reason why we made them distinct is that while a compute needs memory, the reverse is not true. We wanted to be able to have a memory namespace that there's no compute associated with. We wanted to allow NVMe command-based access to memory.
They
With,
both need memory when they're executing, or maybe that's an assumption that you want to make.
so imagine you have memory that you don't want to access over PCIe bar, you want to access it over a fabric. So you could use this to do that. Just pretend the compute namespaces aren't there, right? The memory namespaces can be used for things other than computational storage. Could be purposed for that, and we tried to define it in such a way that that was possible. But I'm not sure if that's answering your question.
Yeah, but you can do the same with the compute one. Also, choose not to. Yeah. Anyway, it's a wide question.
So looking forward, where we have different types of compute. You may have a CPU and a FPGA all in the same device. And the CPU has access to certain memory. The FPGA has access to different memory. Those memories may overlap. Therefore, the memories are each in their own namespace, such that you can associate the appropriate memories with the appropriate compute. If your compute and memory are all in a namespace, that is a compute memory namespace, then you can't have that overlapping of the memory between the two, because now you have memory that is somehow in two different namespaces at the same time.
So for example, if you had that FPGA that had some onboard memory, but also had common memory that it could share with a general purpose CPU, that would be a case like Bill is describing. So if you just have one big blob and it's all equally accessible to anything, you don't need multiple namespaces. You could just create one out of that, if that's what you're asking.
And is there any expectation about the compute namespace that persisted?
What aspect of it are you asking about, whether it's persistent?
Load the program, is that expected that that's backed by persistent memory?
Good question. So there is not an expectation that the programs are persistent today. We've talked about adding support for programs that are persistent, but in the first release, they're volatile. So if you were to reboot, the programs would go away. Sanitize and format also make the programs go away. And we're going to come back and talk some more. We haven't determined yet whether we want to add a future feature to support persistent programs that would survive these things.
You might want to address downloaded versus
So Bill's pointing out that the behavior I described is for the downloaded programs, right? The fixed programs that are kind of pre-installed, you can unplug the power and plug it back in. They'll still be there because they might be in hardware, right? They're not going to go away by doing these kinds of things. But the downloaded programs is more what I was referring to, and they will be volatile.
What's the, I mean, obviously you're talking about specification here, but what's the sort
So one of the things that we've started talking about over the last couple of months is to go to that step. So we had to get the specification to a certain point before we could start writing software. We'd have to throw it away every week or something. So we've gotten it to the point that we're now talking about how do we do that? How do we get together and say, all right, so we want, let's say, Linux drivers for this, and do we want a QEMU thing that emulates it, and what support do we want, and how do we, has multiple companies contribute to that? So we're working on trying to determine how that's done. There's legal things related to that we're trying to work through, but we are talking about that right now. But prior to now, it was kind of at a point where you would just have to keep throwing it away as we keep changing our minds on various things. So I'm not sure if that answers your question, but that's, yeah. Any other questions? How are programs identified? Was that the question? And by identified, do you mean how do you tell them apart, or what?
It would be kind of useful if the example was made a little bit more concrete. For example, coming into this when you say copy data, what's copy mean? What's data mean? Which data? Where? Is copy an actual copy operation or is it virtual method?
Copy is an actual copy command.
I got that from the question we had.
Yep. So you're asking about how are the programs identified in the commands? Or
Download a program.
to download the program?
If you download a program, how do you tell what program to get later? Or how do you call it?
So when you download a program, on the side here you have the numbers like 0, 1, 2, 3. So those are the program indices. And when you download it, you say, I have this program and I want you to download it into slot 3. So once you've downloaded it, you know it was there. You know what you put there. But in addition to that, we have a log page that you can query for each of the compute namespaces, and it will return you back. Index 0 has this program, and there's a small number of fields related to that we'll have there. So for fixed programs, in particular, we're going to have something we're calling a program unique ID, which is a how many bit value, Bill? 64-bit value that we're splitting up in certain ways to be able to specifically identify what's there. So what I said is, like, you download it and you know what you put there. That's fine if it's downloaded. But if it's not, if it comes up and says there's stuff there, how do you figure out what it does? So the idea with these 64-bit IDs is that's a number that you can go and look up what that corresponds to. So we are discussing having a vendor portion, like an OUI, an organization portion, and then some other bits. So if the company is by, if the program is by vendor X, you could go look up vendor X's thing, and program number 5002 means this is a decryption program with this particular algorithm, and this is where the parameters are. You put your inputs here and you put your outputs there. So it's kind of like it's a way to look up, let's say, the equivalent of the API or calling convention for that program.
Do you have any standard debug features to help this out? If I say execute program, it never goes back because it runs to completion. I have a endless loop in there. How do I know? How do I stop it? How do I do anything?
So one of the things in the software group that I'm talking about that we're still working on is figuring out what is needed for that kind of thing. So like if you had a particular format you could download, whether that be eBPF or something else like that, how do you debug it? If it crashed, is there a traceback? Is there what do we do, and how much room does that take to store it, and that kind of thing. So that's some of the things that need to be discussed. So, but overall with NVMe commands, you can have, if the command doesn't return, you can abort that command and that wipes it out. But that doesn't answer the question of, how do I figure out what happened? I wrote this thing and it's just, so that's some of the things we need to talk about. And in particular, what does an NVMe device provide to you versus is there something related to, like if I provide you, let's say, an eBPF engine, what does that engine provide that we can get back to you? And is that in the standard or is that, some side way to do it, something like that? No other questions? Thank you all. Oh, one more.
Just one. So this is very focused on a single subsystem. You guys, anything envisioning for multiple subsystems, multiple devices, memory that's not full?
So NVMe is, the way the things are defined is all focused on single NVMe devices. So what this does is it gives you the building blocks of how each device works. And the thought is that something above that could tie them together, whether that be the SNIA API or something else that would, call the same kinds of NVMe interfaces on A and B and bring them together. But NVMe itself, I'm not sure that it's the right place to pull the multiple device things together, since it's very device-oriented protocol. All right, thanks everyone. Appreciate the questions.